Everybody doing good this morning? We've had a big weather change since we last met. So now we're really in fall. I do believe. You like that? Like fall? Yeah. Yep. Favorite time of the year? I like it until the leaves fall off all the trees, and then I don't like that. I don't like the look of that, so it's a little yucky. I don't know. All right.
It'd be great if they weren't so wet when they fell.
I know. I do hate that too. I have to agree. This rainy weather, don't like that. So it's no fun. But hopefully it'll clear up and be pretty fall weather. At least maybe when you all are out of classes next Monday and Tuesday, right? Everybody knows fall break next Monday and Tuesday. Okay. Last week we were finishing up. In section 7.2, we had done some more with the inverse trig functions. We had talked about the inverse secant, inverse cosecant, inverse tangent, right? You all remember those things? We talked about which quadrants they would be located in. I always worry about that gap from Thursday to Tuesday because it's hard to remember everything, right? So, but y'all can do that. So we talked about where those were located. And how to get those, and how we were going to think about the reciprocal type function to help us out with those. Does anybody have a question starting out there on page 452, 453, where we were working last time? We were doing some calculator problems also last time. Okay, I have a request for 21 over here, so let's do 21. And just see what was going on in 21 here. On page 452... we have the inverse cosine of the sine of 5 pi fourths. Okay. Whoops. I'll switch over. Sorry. Forgot where we were there a minute. Now, before we got to this section, we were working with the inverse of the function of the inverse, those types of things, and we could just pull out the argument as long as it was within the areas we could look. You know, so we were looking in the particular range. In this case here, it's two different functions anyway, so we have to work from the inside out. The sine of 5 fourths pi is going to be what? What's that part? It is negative. Negative what? Negative square root of 2 over 2. And the inverse cosine of that, now it's saying, what angle has a cosine of negative square root of 2 over 2? But because it's asking, you know, inverse cosine, that was how it started out, we're looking in what range are we looking at here? What values can we have?
0 to pi.
0 to pi, right. So what angle from 0 to pi has a cosine value of negative square root of 2 over 2? 5 pi fourths is past pi. Okay? It's going to be 3 pi over 4, the one that's in the second quadrant up there. So 3 pi fourths. That would be the angle that has a cosine of negative square root of 2 over 2. Does that make sense on that one? How we're working from the inside out. We're doing what it says in the parentheses. We're gradually working our way outward there. Is there a question on that one? Is there another one there you wanted to look at?
Can we do number 29?
Yes, 29. On 29, we have the cotangent of the inverse sine of negative square root of 2 over 3. So this one's starting out saying inside here, you know, what angle from negative pi halves to positive pi halves has a sine value of this negative square root of 2 over 3. The problem here is we didn't see any angles that we know about in our unit circle that have that sine value, right? This is one of those that we're going to draw. We're going to say, well, it's going to be some angle theta. So if it has a negative sine value, which quadrant should I draw my angle in? Fourth quadrant, right? If it were positive, I'd draw it in the first. If it's negative, it's going to be in the fourth, because remember, I'm looking from negative square root to negative pi halves to positive pi halves. Okay, I got my words mixed up there. Okay, so if we draw this in here, we know that the sine of theta is negative square root of 2 over 3, which tells me that y is negative square root of 2, r is 3, right? That's what that's telling me, because y over r is the sine. And what I want, though, is the cotangent of that angle. The cotangent of the angle that has that sine. So we've drawn just some general angle that has that for its sine, the negative square root of 2 over 3. And we want the cotangent of that angle. All right, so to get the cotangent, remember the cotangent's equal to what over what? Okay, cosine over sine. If I'm looking at x, y, and r, what will I use? Or x over y. We know tangent's y over x, cotangent's x over y. I need to get my x value here. So x squared plus y squared is r squared. X is what I don't know up here. So x squared plus negative square root of 2 squared is 3 squared. That's x squared plus, what's that give me? Negative square root of 2 squared. What's it going to be? Negative square root of 2 squared. That's the part I'm on. That's just 2. The negative squared becomes positive. Square root of 2 times square root of 2, that's just 2 because it's the square root of 4, equals 9. So x squared is 7, and x is going to be positive or negative square root of 7. Which one?
Negative.
Should be positive, because see how the x comes out on the x-axis? I mean, we're out in the positive realm of x. We do have to think about that when we're getting this part. We want to make sure, you know, that we put in the correct positive or negative sign. All right, so if the cotangent then is x over y, what do we get up here for our answer? What's x? We just found x, right? What's y? Square root of 2, it's negative, and we want to rationalize this, so we'll multiply by what? Square root of 2 over square root of 2. I get the square root of 14 over 2, and it is negative, right? The fraction's negative. So negative square root of 14 over 2. Now, what we were looking at there was the cotangent of the angle that has a sine value of negative square root of 2 over 3. So first we drew the angle that has the sine value of negative square root of 2 over 3, and then from there we calculated what the cotangent would be for that same angle. Is there another question on this one? Okay. Anything else on this problem that's up right now? Okay, I heard 23 also. Right, did I hear 23 over here a while ago? Okay, 23, 25. All right. 23, inverse sine of the cosine of negative 7 pi 6. So first we want to know what's the cosine of negative 7 pi 6. What's that? I'll let you all tell me. It is negative square root of 3 over 2. That's correct. Because that negative 7 pi 6 is ending, it has the same terminal side as 5 pi 6. Right? Are you following on your unit circle? Draw a sketch. If it helps, draw a sketch. Okay? Negative 7 pi 6 is negative 1 pi and 1/6 pi. So that's a little bit exaggerated, I guess, but there's our negative 7 pi over 6. Okay? That's ending as at the same place if I went this way and got to 5 pi 6. So there's pi. That makes sense? When you're looking at that, they're sharing that same terminal side or ending side. The coordinates out there are negative square root of 3 over 2 1/2. That's what we're thinking of. That's where we're not just pulling these answers out of our head. We are, but in a sense, but with reason, within reason, where they're coming from that unit circle, okay? Everything we're putting up here on this type of problem is coming from the unit circle. So what we now have is the inverse sine of negative square root of 3 over 2. So we're asking which angle from negative pi halves to positive pi halves now has a sine value of negative square root of 3 over 2. So what angle is that going to be? Because now we're just looking from negative pi halves to positive pi halves.
Would that be negative pi sixth?
Negative pi 6, right? It's going to be the one that corresponds down here. So it will be negative pi 6. That's correct. Okay. So we're having to go over into that fourth quadrant to get the negative sine value, the angle with the negative sine value now. You may have a question there. That was 23, and I also heard 25. We'll look at 25. It's another one we're going to have to draw. Okay. 25, we have to draw it. Anything else on 23 before I move 23? Yeah, go ahead.
It looks like it's negative pi thirds.
Oh, did we put the wrong one down? What did we do here? Oh, because we were looking at the sine, not the cosine. Right, I'm sorry, I was thinking cosine. Let's go back. Thank you for that correction. I was still thinking on those pi 6 angles. I don't know why. All right, so let's go back. We're looking for the angle that has a sine value of negative square root of 3 over 2. We are looking then here where the sine value is negative square root of 3 over 2. And the cosine value was 1/2, right? So it's negative pi thirds, right? We're that far down, right? Sorry about that. I don't know what I was thinking on that one. I think I was misinterpreting my cosine and sine. Why don't we put 5 pi over 3? Because when we do inverse sine, our answers have to be between negative pi halves and positive pi halves. And 5 pi over 3 is too big. Okay. Yeah, they're ending at the same place, but we're staying within these parameters that have been set up for us. Okay. That's when the problem starts out asking inverse function, inverse sine function, inverse, whichever one we're looking at. We're looking within set parameters there for our answers. I'm saying this for a reason, because we're getting ready to go into something where we'll be back to answering the other way. Okay. I hope there's not a lot of confusion with that, so we'll see. All right, sorry about this problem there. I'm glad you double checked that one for us. I don't know what I was thinking on that one, but is everybody clear on it? Does it make sense? I don't want to leave you hanging. We good on that? So you see why it had to be negative pi thirds instead of negative pi 6. You'd tell me if you didn't, right? Okay. I hope you'd tell me. All right, let's go to 25 then. We said we'd have to draw that one. 25 has to be drawn out, I think. It's the tangent of the inverse sine of 1/3. We don't have an angle that we've studied on the unit circle that has a sine value of 1/3, so we're going to draw us one. It will be in which quadrant? Remember inverse sine, we're looking from negative pi halves to positive pi halves. It'll be up in the first quadrant. We'll just call it theta. If the sine of theta, we're making it be 1/3. Sine is y over r. So again, here we'll have y equals 1, and then we'll have r equals 3. We want the tangent of that angle. We want the tangent of theta is what we're really looking for here. Tangent is y over x. So if tangent is y over x, we need that x value again. X squared plus 1 squared is 3 squared. X squared plus 1 is 9. X squared will be 8. And x will be positive or negative square root of 8. Positive square root of 8. But the square root of 8, we know 4 goes into 8. So we get 2 square roots of 2 there for x. So it makes the tangent be 1 over 2 square roots of 2. When we rationalize, we get the square root of 2 over 4. Let's make it square root of 2 over 4 for that one. Where's a question there? When we draw it, we don't really care what the angle itself is, but we're finding out other information about that angle. Once we get the drawing, we have our x, y, and r, and we can find any of the trig functions that it's asking for. Anything else there on that one? Is this coming together a little better this morning? I'm not sure what was going on with this stuff over the weekend. All right. Let's see. All right, so anything else there from that part? Hopefully some of you tried those calculator problems. If you were using your cell phone calculator in class last time, or if you did not have a calculator, I hope you will go back and try some of those, because I also want you to be able to do the inverse trig functions on the calculator as well. Not this type where we're looking for an exact value, but there were others there that we were practicing with, so please make sure that you're seeing how to work with those as well. Any other questions on this part here on 7.2? The last thing that we did mention last class, or I think we mentioned it, about the inverse cotangent falling in the second quadrant as opposed to the inverse tangent being in the fourth. We talked about how we had to add pi to whatever we got there on the calculator, right? We talked about adding pi. We did. I'm pretty sure we did, didn't we? Somebody confirm it? Yes. All right. You are making me a little nervous out there. Okay, so we talked about having to add pi if we had the inverse tangent of a negative value. So remember the inverse tangent of it, not the inverse tangent, inverse cotangent. I'm getting all my words screwed up today. Okay, so the inverse cotangent, for example, on number 55, the inverse cotangent of -3/2. That's saying what angle has a cotangent of -3/2, but we know our inverse cotangent was defined from 0 to pi, right? From 0 to pi. Okay. Now, whenever we looked at these, though, we said, well, that means the cotangent of some angle is -3/2, and we were in the process of using the reciprocal functions to get there, because we said if the cotangent of an angle is -3/2, then the tangent of that angle will be -2/3. That would make sense for us. The tangent is the reciprocal of the cotangent. So if we use the inverse tangent on our calculators, this was a calculator problem, okay. If we use the inverse tangent on the calculator here to get this value, and remember our calculator was in radians, this gave us some negative angle that was down here in the fourth quadrant. What did it give us? Somebody have that? Negative point something. What was it? Inverse tangent of -2/3. You're putting it in your calculator like this. Second tangent for the inverse tangent. -2 divided by 3.
Like 0.588.
Okay, 0.588. So we'll put -0.59 here. But the problem is that's an angle down in the fourth quadrant, and we need this. We need our angle to be from 0 to pi. So we need it to be, in this case, if we're having a negative cotangent from the original problem, then our tangent would also be negative, which puts us in the second quadrant. So we want this angle here that I just drew out there. And to get that, we said we could do what?
At 180 degrees, or
Yeah, add pi. You can just add pi, that's right, because when you add pi to that, it's the same as saying pi minus that 0.59. We know this little piece here is also going to be 0.59. So if we take pi minus that, or what you got, since that's on your screen, plus pi, what does that give you? Approximately 2.55. Okay, so that's what we're saying our answer is. We're looking at the angle that's 2.55. We said the only time we have to do this process is if we have the inverse cotangent of a negative value. That's the only time. Inverse cotangent of a negative value. Okay. So I just want to remind you about that. If it's anything else, we can just go to that reciprocal type inverse function and use the reciprocal of the argument. Anybody have a question there? So today I want to go into section 7.3 and talk about trigonometric equations. We want to be able to solve equations today. We've solved some inverse trig equations already back in 7.1. So I want to remind you about those as well. But then we're going to solve some other types of trig equations. In fact, the first part of what we're going to do is going to look like algebra. We're going to do a little algebra here just to remind us of some equation solving techniques. So we're going into section 7.3. Trigonometric equations. And we want to remember a few things. Remember when you had things to solve like 2x plus 5 equals 15? Remember things like that? Yeah, y'all remember those. Everybody's worked with those. I'm just bringing this back up because we're using the same equation solving steps. I don't want y'all to say, I've never seen anything like this before, just because it has a trig function in it. This one doesn't, but when we get to the ones that do, we're using the same steps. What's our goal when we solve an equation? To get the x by itself, right? To get the variable, whatever the variable is, we want to know what that variable is equal to. We also want to know all possible solutions. Everything that could possibly work back in that equation is what we need to have. This here is just a very basic type of equation. So if we, you solve it by subtracting 5 from both sides, you get 2x is 10. You divide by 2. And all this is in an effort to get x by itself. That's your goal. These are the steps we follow to get x by itself. We remove anything from the side where x is. We remove anything that's being added or subtracted. And then we've got that term right with the x, the coefficient of x, that 2x. So we had to divide that out. Remember also you can check your equations by plugging the value you get back into the original equation and making sure that it causes the left side of the equation to equal the right side. So we can always do that as well. We also want to remember here, let me go back a minute, the ones that we already did back here because you're using the same steps overall. We did some in 7.1. We had one like this. We had 4 inverse sine of x equals pi. Remember those? Okay, 4 inverse sine of x equals pi. And to solve that, we divided by 4, again to clear that out. Our mission is still to get x by itself. Now on this one, what we did though is we took the sine of each side. I just didn't leave enough space to do it well. And we got x equals the sine of pi fourths. But the sine of pi fourths is square root of 2 over 2, right? So that would be our solution here for this equation. And there's another type I want you to remember also. Okay, another type of equation before we get into the trig equations. Is everybody okay so far on these 2 equations we've looked at? We're doing algebra. How about this one? X squared minus 5x plus 4 equals 0. What type of equation is this one?
It's a quadratic.
It's a quadratic equation, right? Why is it a quadratic equation?
Because you got a parabola out of it.
Okay, when you graph it, its graph will be a parabola. It has that x squared term. It's a second degree equation. The highest power on a variable is a 2. So we see that as a quadratic equation. We can split a quadratic equation up into, well, basically it's got 4 little pieces to it. Something x squared plus something x plus a constant equals 0. So we see 4 parts, thus, quad, you can think of it that way. Sure, they don't always have all 4 pieces there. They might skip a term, but it's there 0 whatever, that term. Now, how do you solve a quadratic equation?
Foil.
FOIL. When you say FOIL we normally think of as multiplying out 2 polynomials, but I think where you're going with that is backwards on the FOIL, which is factoring, right? So factoring. Factoring is probably the most common way, and it's the way we want to use, if at all possible. In order to use factoring to solve a quadratic equation, the equation must be set equal to 0. So if it's not already saying equal 0, you have to make it be. There are other ways we can solve quadratic equations. You may know another way?
Quadratic formula.
The quadratic formula. That's another way. I would try factoring first. Generally, we use quadratic formula if the equation cannot be factored, if the polynomial itself, the trinomial, is prime, okay, and does not have the factors. Do you all remember the quadratic formula?
I think it's b squared plus or minus the square root of negative b plus 4ac divided by 2.
Okay. Did you give it to me in that order? You gave it to me a little different, didn't you?
I got it wrong.
You had b squared, right? So we have negative b plus or minus the square root of b squared minus 4ac over what? 2a. Negative b plus or minus the square root of b squared minus 4ac over 2a. Those a, b's, and c's are coming from up here in our original quadratic equation, and it does have to be set equal to 0 again. To use the quadratic formula or to use factoring, your equation must be set equal to 0. And I'm going to put up just another method that we sometimes use to solve a quadratic equation. And it may not be as familiar, even though you might recognize it if you actually saw it in a problem. But it's use of the square root property. And basically what it does is if we have one side being squared in the equations, one side is squared equals something, we can take the square root of both sides, okay, to get our solutions here. So, for example, if I have x squared equals 25, instead of setting that equal to 0 and then factoring it, which I could do, instead of doing that stuff, what if I take the square root of both sides? Because my goal is still to get x by itself. Now, the clincher here is, if I do this property, if I use it, what do I have to do? Remember, I want to get all possible solutions.
Do the positive and negative.
I have to put in that positive and negative, right, to account for the positive or negative values that I could get out of here. So the square root of x squared is x. I get plus or minus 5 here. I'm saying that positive 5 and negative 5 are both solutions to my original equation. My original equation was x squared equals 25. If I plug in 5, 5 squared is 25. If I plug in negative 5, if I square negative 5, I also get 25, right? We're trying to get all possible solutions. So when I take the square root of both sides here, I want to insert in that plus or minus to account for all possibilities. I'm showing you these because we could use these methods as well on some trig equations here in a little bit. We have some trig equations that look like quadratic equations. Okay, they're quadratic in form. This one up here that I've got up here now, it's an algebraic equation, x squared minus 5x plus 4 equals 0. We should be able to factor it. Okay? Whether you can factor or not, if you really want to use the quadratic formula, well, that's up to you. I don't advise it, but you can. It still works. If we're going to factor, remember the first thing you look for is there something in common? Greatest common factor. There isn't one here. So we just go ahead and say this is a trinomial. So I'm going to look at factoring it in that so-called backwards FOIL method. FOIL is what we, that's that little acronym that we use for multiplying out two binomials. We're really just using the distributive property. That's what we're doing, isn't it? Everything in the first set of parentheses has to get multiplied by everything in the second set. Now, whenever we factor, and the reason I'm looking at this in a little more detail, we assume you know how to factor, that you've already been taught that when you're in this class. However, I see a lot of problems with factoring in this class. Okay, not just with you all, but in general when I teach Pre Cal 2. Okay, so factoring is one of the probably most hated topics, I guess I could safely say, in an algebra class. Does anybody agree, disagree? It just seems like a struggle type topic. Factoring and anything with fractions. People don't like those things. Okay, so we're going to try to, make sure we remember how to factor here. What we're looking at first are these first terms. Okay, the first term times the first term has to give me the first term up here in my trinomial. That's not too bad on this one. X times x is definitely x squared, and I think everybody's good with that. The last term times the last term has to give me the last term. Now, it's also true, if my polynomial says 1x squared, if it says that, then I'm looking for values that I can multiply and get the last term, that positive 4, that when I add or subtract them, somehow combine them with addition or subtraction, they will give me that middle term. So I want numbers I can multiply and get 4, but when I combine them through addition or subtraction, I get 5, actually negative 5 to be specific. But first I might just want to think about my values. What can I multiply to get 4 but add to get 5?
1 and 4.
Yeah, 4 and 1. Okay. It's like a puzzle. We're filling in the pieces here, okay? That's what we're doing. So we've got our 4 on the end. Now it has to be a positive 4 when I multiply, but when I do my outer and inner product there, I have to get that negative 5x for the middle. So what are my signs going to be? They both have to be negative. So that when I do my outer product here, I get negative 1x. My inner gives me negative 4x. When I combine those, that's how I get that negative 5x up there in the middle there. Okay, that's where that comes from, the OI part of FOIL, right? That OI part, outer and inner parts. You can always multiply back out what you have here and make sure you have the thing. It is important that our equation was set equal to 0 from the start. We are using here what's called the zero factor property. So that when we multiply, if we're multiplying two factors and we get 0, at least one of those has to be 0. If we have anything else over on the other side, we can't say one of our factors has to be this number. If we have factor times factor equals 6, that doesn't mean one of them has to be 6, right? It could be 2 and 3, something like that. All right, since one of these has to equal 0, we're going to set them both equal to 0 here and solve to get our solutions for this equation. Our solutions turned out to be x equals 4 and x equals 1. Again, you can check each of these and plug them back in up there. We have 2 solutions here, though. One at a time, you can plug back into the original equation. So you may have a question. This is like old times right here, okay?
The square root property problem that you did has nothing to do with this one, right?
I did not use the square root property here. That's correct. If I want to use the square root property here, it goes along with another method we have. It's kind of a part of a method we have called completing the square. Have some of you used completing the square before? Where you have to take half the coefficient of x and add that? Yeah. Well, I didn't go into that one today. So, okay. We'll just use the square root property where needed. I'll show you an example here in a minute that will use it. This one did not use it. This was just strictly factoring. Okay. Overall, we want to use factoring if it's possible, or we try to. Anything else about factoring in general? If it's not a 1x squared up front, then we cannot say, what can I multiply to get the last term that will add to get me the middle, because that first coefficient is going to come into play also, and it's going to help get that middle term. So you might have to do a little bit more guess and checking, right? Go ahead.
How did 1 and 4 give you plus 4?
I'm sorry?
How did 1 and 4 give you plus 4?
Okay, if I go back and FOIL this thing out, let me write it down here, x minus 4 times x minus 1. What I'm really doing here, and this is where I want to illustrate that this is the distributive property, because some people say, well, I never understood FOIL. I don't know, maybe that's somebody in here. But I take this x here, I'm going to multiply x times the x over there. I get x squared. Then I'm still working on my x. I'm going to multiply it by the 1 over there. I get minus 1x. I'm finished with the x now. Now I'm working on the minus 4. Minus 4 times x is minus 4x. And minus 4 times the minus 1 is plus 4. The idea is I have to multiply everything in the first set of parentheses by everything in the second set. So when I have this minus 4, the sign in front of the number goes with it. So minus 4 times minus 1. I don't know why I put that one up in there. But minus 4 times minus 1 will give me that plus 4 on the end. These two combined to give me the minus 5x. Okay, so that's where it's coming from. Any other questions here on this one? Anything else on that part? Well, we want to be able to do this with trig functions also, if they're involved as well. So instead of saying x squared in an equation, we might see cosine squared x, cosine squared theta. And we want to be able to treat it like we just treated that x squared, though. Okay? So let's look at some trig equations. Let's put some trig functions in now and see what we can do with those. This again is in section 7.3, and let's pull out over on page 460. We won't make it too bad here at first. Let's pull out number 12. 1 minus cosine theta is equal to 1/2. And I want to solve that. Remember, my goal in solving an equation is to get the variable, which theta is the variable here, by itself. So I want to get theta by itself. What am I going to do?
Subtract 1 from each side.
Subtract 1. Now I have negative cosine theta equals negative 1/2. Now what? Okay, you said multiply by negative 1. You could also divide by negative 1 if you wanted. So I'm multiplying by negative 1. I'm doing that to get rid of that negative sign. So I've got cosine theta equals 1/2. The cosine of some angle equals 1/2. Now, here's the thing. I forgot to tell you this part here. In the textbook, they say to solve for theta on the interval from 0, they've got it like this. 0 is less than or equal to theta is less than 2 pi. From 0 to 2 pi. Because with these functions, we can have an infinite number of solutions. You know how they're periodic and we just keep going around that unit circle? We could just keep coming up with all kinds of angle measures, just larger and larger, or smaller negative angle measures. But we're just going to look one revolution from 0 to 2 pi. We're going to include 0, but we're not going to include 2 pi. Okay, so this is just how it's given to us in the textbook. This is where we're going to be looking for our answers. So here's the part that gets really tricky then. We've just come out of a section where it said, find the inverse cosine of 1/2, and we knew that that meant when they asked us that question to only look from 0 to pi. We're doing something different now. We want to find all possible solutions where the cosine of the angle would be 1/2. All possible solutions from 0 to 2 pi. So looking at all 4 of those quadrants when we're solving an equation. What I want to really stress here is the difference in solving an equation and just having an inverse question thrown at you. Okay? Because some of you may look at this and say, you know what I would do with this to get rid of cosine is I would take the inverse cosine of each side. because we're looking for an angle, correct? But we're the ones putting in the inverse cosine, and we know we're solving an equation, so now we're looking from 0 to 2 pi. Okay, so even if you decide to do that. Or you might just want to think, what angles, still thinking kind of along the same line, what angle or angles have a cosine value of 1/2. That's what we're looking for, right? And those angles from 0 to 2 pi, where that happens. So which angles have a cosine value of 1/2? Pi thirds does, right? Pi thirds and 5 pi thirds, right? Have that cosine value of 1/2. We are looking at all the angles where that happens from 0 to 2 pi. So I'm hesitant to even write up that we're doing the inverse cosine, even though technically we are doing the inverse cosine. We're looking for an angle. We are doing that process. But because we're looking for all solutions to the equation, we have to adjust in our minds. I'm looking for solutions to an equation now from 0 to 2 pi. And I need all possibilities. If they just threw the question out there that said inverse cosine of 1/2, now you're only looking from 0 to pi. See the difference in the two questions? One, you're solving an equation for all possibilities. The other, they're just throwing out, this is, you want the inverse function, so you're only looking from 0 to pi. Okay. Any questions on this equation, generally solving it? Go ahead. Where did the 1 go? What one? Oh, the one at the very beginning. Okay, she's looking up here. This one right there, right? We subtracted 1 from both sides, and 1/2 minus 1 gave me negative 1/2. Okay, so we just put it over there on that side with the 1/2 and actually combined it. What else here? Let's try another one, okay? Let's look at another example. I want you to see some different types that you might have in here that have some very That's a 0 on the right side. Excuse me just a minute. Y'all try that one, okay? How many answers are you getting? I hear 2 answers. Any more, any less? Anybody? All right, let's add 3. We have 4 cosine squared theta equals 3. We're going to divide by 4 to get rid of that. So now we have cosine squared theta is equal to 3/4. What are we going to do now? We can take the square root on this one. This one's using that square root property because we have something, the whole side is squared equals something else. Okay, so let's take the square root here on both sides. On the right, we'll have to put in that plus or minus, though. Don't forget that. So this is what we had. We're taking the square root of both sides. That's giving me the cosine of theta equals plus or minus, what's the square root of 3/4? Square root of 3 over just plain old 2, right? Square root of 3 over square root of 4. We want to know those angles where the cosine is equal to positive or negative square root of 3 over 2. Technically, what we're doing here is we're putting in the inverse cosine, but we're putting it in there, and we know we're looking between different parameters now. All the angles that have the cosine values of positive or negative square root of 3 over 2. What angles are those? Pi 6, 5 pi 6, 7 pi 6, and 11 pi 6. We actually get 4 answers here. There's not going to be any set number of answers on these trig equations. Sometimes, you might get 1, you might get 4, you might get 2, you might get 3. You don't know. So there's not any set number of answers. Now remember, we were just looking, though, from 0 to 2 pi for our values. Okay. Otherwise, we could keep going on around the circle and say, well, we've got 13 pi 6, right, and so on, because those would be true. But we're cutting it off there. Questions on this one, on using that square root property? Go ahead.
When we take the square root, actually it was like cosine squared, do we always have to put the positive or negative up there?
You put the plus or minus on the side with the numbers, okay, the numerical side there. Okay, we're taking the square root of the cosine squared to get just cosine. And then on the other side, to account for all possible solutions, we put in that plus or minus to take into account the positive and the negative. Okay. So we do have to do that when we take the square root of both sides. The only time we don't do that is if we're in the context of a problem where maybe we're only looking for distance or something like that. Okay. And then we know we're looking for a positive in that case. So if it doesn't apply to the context of the problem, we only think about the one that would. What else there on this one? Anything else on this particular one? All right. Let's see what that's square root property being used in that one there. So let's switch it up here a little bit. What about this one? 2 cosine squared theta plus the cosine of theta minus 1 equals 0. What are you going to do with that one? It looks like a quadratic equation, doesn't it? In fact, what some people will do is they'll, instead of cosine theta, they'll use x's, and they'll say 2x squared plus x minus 1, but then at the end, you'll have to come back to it being your cosine theta. I would rather just leave it cosine theta myself, but that's up to you. But we're going to say the first terms in each set of parentheses have to multiply and give me 2 cosine squared theta. So that's just going to be like 2 cosine theta times cosine theta, right? Does that work? That gives me 2 cosine squared theta. The last terms in my parentheses have to multiply and give me 1. So that's going to be, whoops, I can't write with an eraser. 1 times 1. Now, this middle term has to come out to be a positive 1 cosine theta. Remember, it comes from this product and this product. So I have to figure out, how do I want my signs to be? I can see I've got to have a positive and a negative some way to get that negative 1 on the end. So how do I want my signs so that I get a positive cosine theta in the middle there? Okay, so you tell me to put a plus in the first parentheses or in the second? No? Second one, okay. because she said put the plus in the second one because that's where the 2 cosine theta times 1's coming from. That gives me a positive 2 cosine theta. This part here gives me a negative 1 cosine theta. Together, those will give me a positive 1 cosine theta that I wanted up here. See how we're getting that middle term? So we've got our factors here. We're going to set each factor equal to 0 and solve those. See what you get. Solve those out for me. All right, so we've got, what do we have here? 2 cosine theta is 1. Cosine of theta is 1/2. Where's the cosine equal to 1/2? Pi over 3. Where else?
5 pi over 3.
5 pi thirds. Okay. On the other part, we have the cosine of theta is negative 1. Where's the cosine of theta equal to negative 1? We're at pi. So all of these are answers. Okay. There's 3 answers for this one. So that's with factoring. Anybody have a question on this one with factoring or any part of it? Anybody get lost in the problem?
So you could do this with the quadratic equation also.
If you really wanted to, you could work with it with the quadratic equation. But you're going to come out. Yeah, you're going to come out then, you know, you're thinking of those cosine thetas as x. So your a is 2, your b is 1, your c is negative 1 here. You would plug in, but then whatever you get, you're going to have to say the cosine of theta is equal to, it'll give you 2 values, because again in the quadratic formula you have that plus or minus in there. So you're getting 2 separate things. So you're going to have to remember to put back in the cosine of theta is equal to whatever those things are you get and still figure out theta. My experience has been that a lot of times students forget to put it back into terms of cosine theta. And so they'll leave just the answers they get there. But it would work. Anything else on this one? There's all different types of equations here, so I'm just trying to highlight some things you'll want to think about when you're working through these. The 5 cosecant theta minus 3 equals 2. This one has cosecant in it. That's why I'm throwing this one up here. That shouldn't be a big deal for us, but just to make sure it's not, let's throw it up here and see what we've got. Pretty basic steps on this one, right? Pretty basic steps. Let me give you just a second to try it. All right, how many answers? One answer. One answer this time. Okay, you added 3, I'm assuming. 5 cosecant theta equals 5. You divided by 5. We did it to clear that 5 that's with the cosecant theta, but we're also getting a 1 on the right side here as well. Now, it's in terms of cosecant, but when I see cosecant, I'm probably going to start thinking about what? Probably the sine. more than likely I'm going to think a little bit more about sine, cosine, and tangent instead of secant, cosecant, and cotangent. So here it's telling me the cosecant is equal to 1. That tells me that the sine is equal to 1 as well. So where's the sine equal to 1? That's going to be my answer.
So pi halves.
I put pi halves, right. It's not too bad, was it? Think about that one. If it comes out something about secant, maybe you want to think about the cosine's equal to whatever the reciprocal is. It'll make your work a little bit easier, I believe. All right, I have one other one here I want us to look at today. Okay. Everybody okay on this one we just did with the cosecant? All right, one other thing here. This one is 64, and it says this. Cosine squared theta minus sine squared theta plus sine theta equals 0. Does anybody have a problem with this one? What is the problem with this one? There might be a little bit of a problem with it. Go ahead, Clay. All right, so we have 3 thetas. That may or may not be a problem. What's making it be a problem with us having 3? What's that? We've got 2 different trig functions going on here. We've got a sine and a cosine both being involved. We hadn't seen that, right? That might be a little bit of a problem because how are we going to get that theta out of there? You know, how are we going to factor if we've got the cosine and the sine in here and they're both squared? So I think that's where you were going with the extra thetas as well. But we've got some different things going on here. It would be nice if we could have this all in terms of the same trig function. We can do that. We can work a little magic here and manipulate this thing because you all know your trig identities. So you're laughing. All right. You know the Pythagorean identity specifically. Refresh my mind on that Pythagorean identity. Somebody tell me what it was.
X squared plus y squared is equal to r squared.
Okay, well, what about in terms of cosines and sines? Okay, you are correct on x squared plus y squared equals r squared, but let's put it, since we're working with cosines and sines, let's put it up here like that and say cosine squared theta plus sine squared theta equals 1. So which one would it be easiest here for me to substitute or replace? I want to get rid of that cosine squared theta, right? Because the other 2 both have sines, so sines went out, majority rules here. So cosine squared theta happens to be equal to what?
1 minus sine squared theta.
Yeah, it's equal to 1 minus sine squared theta. So instead of cosine squared theta there, I want to use 1 minus sine squared theta. And I'll just leave the rest of my equation like it was. I'm just replacing. I'm making a substitution to make it a little bit easier to work with. If I make that substitution, I don't have to deal with 2 trig functions. I can only deal with that one. I only have to work with sine. So that's the goal of doing this, of plugging that in there. Well, what does that give me now? This still looks pretty involved. I've got some like terms I can put together now. So I've got 1 minus 2 sine squared theta plus sine theta equals 0. Is this a quadratic type equation?
Yes.
It is, because I've still got that sine squared theta. And typically when we're working with the quadratic type equations, we want them to be in ascending or descending order as far as the powers of the variables are going. You know, we want to start with our x squared, and then our x, and then our constant, that sort of thing. So what do you want to do here? Rearrange a little bit? How would I rearrange?
Negative 2 sine squared theta plus sine theta plus 1 equals 0.
That makes it where I can look at it and factor it better, okay? The only thing I wouldn't like with this, I don't like factoring with a negative at the front. Some of you may not care, and it doesn't matter, but it makes it a little easier if you don't have that -2 at the front. But we can get rid of that also, can't we? How can we get rid of that?
Divide by -1.
Yeah, we can divide the whole thing by -1 if we want. And that's just an extra step if you don't like that. It's a cosmetic thing more than anything. So 2 sine squared theta minus sine theta minus 1 equals 0. It just changes all the signs in there. Let's factor it then. I'm going to have 2 sine theta times sine theta, again, to get 2 sine squared theta. I'm going to have a 1 times a 1, again, to get a 1 on the end. It's got to be a -1 when I multiply. That last term there, that last sign is negative. Right here. That's negative. Whoops. So I have to have a positive and a negative. How are they going to go? Positive in the left one this time. Okay, because why? That has to be negative sine theta. So I've got sine theta minus 2 sine theta. Always look at what you're getting with that outer and inner part. You don't have to draw those little curves that I'm drawing, but you can if you want to. Helps you see what you're doing there. You've got a sine theta coming from the middle part, and the 2 sine theta times -1's -2 sine theta out there on the outside. So -2 sine theta. Just write it in here, -2 sine theta and plus 1 sine theta together gives me that negative sine theta that I have in the problem. Now I'm going to have to set each of these factors equal to 0 and solve. So I'm going to have 2 sine theta plus 1 equals 0 and sine theta minus 1 equals 0. So 2 sine theta minus, equals -1. Sorry, I said that wrong. Sine theta equals -1/2. The sine's going to be negative, then I'm down in the third and fourth quadrants. If the sine's negative, if the sine's -1/2, what angles would those be?
7 pi 6.
Okay, 7 pi 6 and 11 pi 6. Whoa. I hit that again, it makes it smaller. 7 pi 6 and 11 pi 6. Let's bring that down a little. What about over here? The sine is equal to 1. So theta is going to be what? Pi halves. So that's what we get there. I want you to see this one because I want you to see if there's 2 trig functions involved, many times there's a substitution you can make so that you can put it in terms of 1 trig function. Okay, and that's what we were looking at here, is how to do that, how to put it into 1 trig function. Anybody have a question on number 64? Now, are you all seeing the difference in solving the equation from 0 to 2 pi versus just having an inverse question where we have to think about, from 0 to pi, negative pi halves to positive pi halves, those things? You're seeing the different types. To make sure you see those types, I'm going to post for you a little, it'll be like a little homework assignment. Instead of doing an in-class quiz like we did with the unit circle, I'm going to post something later today that won't be due until after you come back from fall break, okay? You don't have to turn it in until next Thursday, but I will want you to print it off and do it just to let me know that you see what's going on with that. And it's going to have some inverse trig questions as well as some equations on it, okay? I'll send you an email when I get it on there later, just so you'll know it's there with some better instructions. But I just want to make sure we're seeing the difference in what's going on with what we're working with because of these being so close together in the textbook. Here's some problems you can practice with from section 7.3 over on page 460. I highly recommend you do some practice here on 11 to 29 odd and 57 to 79 odd. And we'll see how that goes when you come back in on Thursday. And on Thursday, we'll be going into section 7.4 on trigonometric identities. And you're saying, well, we already did identities. We're going to see some other things about identities. You'll want to be here for that, okay? Well, you might not want to, but you need to, okay? So come back Thursday, and we'll work on that then, okay? Any other questions today? We good today? You all have a great day then. Thank you.
Try to